have similar figures notes here. And as you remember in the first video, we looked at the ratio rule for similar rectangles, similar figures. And we discovered that the ratio of the areas is the square of the ratio of either the sides, common sides, corresponding sides, or the perimeters. If we look here, we have two rectangles that we can easily figure out the area. The first one would be 10 times 16, which would be 160. And the second area would be 15 times 24, which is 360. 160 over 360 reduced down would reduce down to 4/9. You could simply do that by getting 16 over 36, which is knocking off the zeros from this 160 over 360, and then reducing 16 over 36 by dividing by 4, which would give you 4/9. So right now, we already know that the ratio of these two areas is 4/9, but sometimes they're not going to give you the second set of sides, and you have to use the ratio rule that we're going to use right now to discover that. So what we learned in the previous video was that if we find any set of corresponding sides, like if we do 10 over 15, this ratio does reduce down if we want to do that. If we divide everything by 5 to 2/3, right? Divide each of these by 5. Well, if we take 2/3, which is the ratio of the sides, oops, let me just fix that. Okay. If we take 2/3 and we were to square this ratio to get the ratio of the area of the two figures, right? This is side over side. This is going to give us our area over area. And if we square 2/3, we're going to get 4/9. This is our area over our area. Ratio over two areas, I'll call this 1 and 2. We'll call this 1, 2, and 1 and 2. The same answer we have here, we got when we actually figured out the areas. But like I said, they're not always going to give you all the dimensions, and sometimes we're going to have to use the area or the ratio of the sides in order to determine this. Had we chose 16 over 24, we could have reduced that fraction down as well by dividing by 8. We would have got 2/3, and the 2/3 squared would be 4/9. The same thing we have here. Okay, so if we scroll down, let me adjust this. Okay, if we scroll down here, let's take a look at number 2. So here, notice we're not given both dimensions of rectangle A and B. Let's see what it says. Rectangles A and B are similar and are drawn to scale. If the area of rectangle A is 88 millimeters squared, what is the area of rectangle B to the nearest square millimeter? All right, so if you think about what we know we can take advantage of the ratio of the two sides. Now, by the way, one thing we should always check, we're in the same unit of measure, millimeter, millimeter, and millimeter. It's something we need to check as we do these problems. So if we take a look at, side of A over side of B, these two ratios, or these two values for our ratio, are 16 over 30. Now, sometimes it's easier to reduce the ratios, sometimes it's easier to keep them as they are. But for this one, if we just reduced it, just so you know, we can divide everything here by, let's say, 2, and we would have 8 over 15. So whether we want to use 8 over 15 or 16 over 30, it won't matter because it's just the same value reduced down. So what we learned was if we take the ratio of the two sides of these rectangles, so I'll just do the 16 over 30, but you can definitely use 8/15. And if we square this ratio and set it equal to the ratio of the areas, and we already do know one of these areas, this rectangle has an area of 88 millimeters squared. So if I put it on the same level as the side 16 in the numerator, whoops, there's an 88, and we put x down here so we can solve for the missing area of rectangle B. If we square these two things, we get 200 256 over 900 equals 88 over x. If we just did 16 over 30 equals 88 over x, it would not work. We know the ratio of the sides are not the same as the ratio of the areas. When we cross multiply, okay, we're going to get some big numbers, of course. We have 88 times 900. That's 79,200. And when we multiply 256 times x, well, we just get 256x. And then we divide by 256, we get 309.375. So x is equal to 309.375 to the nearest square millimeter, which would be 309 because the decimal is 0.375. And this is squared because, of course, it's area. Okay, so this is how you can go about determining either the missing area or even a missing side if we had to. Let's take a look at number 3. Okay, number 3. Figures E and F are similar, so they kind of look like two whales or something. I'm not sure what these are, but they're two polygons. If the area of figure E is 120 millimeters squared, what is the area of figure F to the nearest square millimeter? So they want answers in millimeter. Notice how this one is in centimeters. So when we travel from centimeters over to millimeters, and I know we learned this in class, right? We would move the decimal over one to the right, but there's other ways that we can show how to get that dimension. I know we've gone over the metric scale with you and how we convert that, but this is 24 millimeters. So now when we're comparing these, everything is in millimeters, and this is the area of figure E. So this area is 120 millimeters squared. So if we do our ratio, as we've learned before, side over side, 24 over 15, and we square the ratio of the sides, it's equal to the ratio of the areas, which is 120 over x. You might want to take a minute to see if you can solve this on your own. Pause the video and try that. So 24 times 24 is 576. And 15 times 15 is 225. And that's equal to 120 over x. Again, cross multiply here. And if we do 120 times 225, we get 27,000. And that's equal to 576 times x. We divide that 27,000 by 576, we get 46.875. So I'll write that out. You can see the decimal. And if we round it to the nearest square millimeter, this would be 47 millimeters squared. This is our area of figure F. Okay, so you can try the rest of these here. Oops, let me scroll down. We've got similar shapes here, and again, it's the same idea, right? You're making sure things are in the same unit of measure. We've got centimeters, centimeters, and the area of ABC is 30 centimeters squared. That's not my best M I've ever done, but there you go. So once again, you're trying to find the area of CDE to the nearest square centimeter. We're always checking units of measure, so I'll do this one really quick. We've got 11 over 4. We're going to square the ratio of these two sides and set it equal to 30 over x. We get 121 over 16 equals 30. Let me redo that. we go. 30 over x. We cross multiply. We've got 121x equals 480. Okay, here we go. And we divide this by 121. Oops. 480 divided by 121 will give us 3.9669. So we'll round this to the nearest square centimeter, which would be 4 centimeters. Okay. So I hope this makes sense. I'm just making sure I did this math right here. Something didn't seem right. Area, yeah, I guess. We could, I don't know. Obviously, that's the length of the one side, so I just wanted to make sure everything was right here. Okay, I gotta put the square down. Okay. If you have any questions, again, you can ask us, in class, pull us aside, or come see us after school. But this is the idea. So I hope this made sense to you guys.